Okay. So, looks like I'm having difficulty, so hopefully you guys can still hear me. Again, if this doesn't really work out, I will be posting this video at a later date, so if the stream does get too foggy, then just feel free to check out the video when I post it. But again, I'm going to start here with the first question, which is finding the lateral earth pressures, passive and active, for this diagram here. So I'm going to start by finding the slope, which we're going to need. So the slope, this is question 1. And this is a retaining wall. So first we need to find our slope. And the slope, I'll just quickly draw the diagram here. You guys can see what it looks like. So this here is our slope, beta. So beta would be equal to the inverse tan of our opposite over adjacent, which is 1 over 1.75, which is equal to 30 degrees. Now, because we have this slope, we use our big long equation for active earth pressure. So that Ka is equal to cos beta times cos beta minus square root of cos squared beta minus cos squared phi over cos beta minus, plus the root of cos squared beta minus cos squared, phi. And when you plug all those things in, you get cos 30 times cos of 30 minus the root of cos squared 30 minus cos squared, I believe it's 37 for our phi, over cos 30 plus the root of cos squared 30 minus cos squared 37, which gives us a Ka equal to 383. Now, because the angle of beta and the angle of beta for the passive force are not equal, because there's a plant here but there isn't, Ka times Kp does not equal to 1 in this case. So what we're going to do then is, to find Kp, we're going to use the equation in our notes, which says that Kp is equal to tan squared of 45 degrees plus, looks like I had another technical difficulty there. Hopefully that you guys didn't miss anything. Times the cos of 30. And that gives us 547 pounds per feet. And our active is 4,104 pounds per feet. Answers there. So again, the main big difference is your calculations for Ka and Kp. They change when you have a slope. So in tutorial, our slope was like this, and we didn't have this extra bit of soil, but now in this one we've got this extra bit up here, and so we need to account for that slope. Now, question 2 of the tutorial is a slope stability question. This was a question that was found on last year's midterm, so I'm just going to quickly draw a diagram that I'm going to reference as I go through the tutorial. So if we look, this over here. So if we look here at our question, we're trying to find the factor of safety against the failure across here. So this is all clay. This chunk here, we actually don't have anything because it's kind of like as if it was over here. And so we need to know the areas of these angles to find out what our weight is, which in our equation, which I'll get to in a second, we need. So I'm just going to finish labeling this. So this is our beta, which is 30. If this whole angle here, given in our diagram, is 80 degrees, and this is 30, and that means that this here is 50. We know this is a right angle, so this must be 10. And then for the purpose of what I'll be going into, we know that this whole angle here is 60 degrees, so our theta 1 is 60 degrees, and our theta 2 is 10 degrees. So in your notes, you'll be able to find the slope stability. In your notes, you'll be able to find an equation for one of these like triangular soil diagrams, which has this equation. So alpha, this isn't beta. So in our equation, sorry, this is my fault. In our equation, it's given as alpha, but in the diagram, it's given as beta. They're just variables, so you can ignore the diagram and say that that is alpha, because that's what you're going to need. So our cohesion is given at 50 kPa. Our length is the length of the slope failure face. And in this case would be E. So from here to here. Oh no, where's my backspace? Okay, I'll just draw it again. So our AD, length AD, is equal to 5 over sine 30, which gives us 10 meters. So that's our value for L. Our W, so our W is going to be the unit weight times the area of ACD, this triangle, the area of that triangle. But because of this, an easy way to do it is to say that ACD is equal to minus the area ABC. So first, I'm going to find ABD, which would be so to find that, first we need to find what the length BD is, because we're going to do AB, which we know. So here, AB times BD over 2. AB we know is 5. So BD then, we know that tan of theta is equal to opposite over adjacent. So if we're looking at ABD, the angle there is 60 degrees. So tan of 60 is equal to our opposite, which we want to know, which is BD, over 5, which is our adjacent. So BD is equal to 8.66 meters. And then we're going to have to do that again for our ABC triangle. So tan of 10, because this here is 10, is equal to our opposite, which is our, close this, make this bigger here. So our opposite, which is BC, which we need to know, over our adjacent, which is 5. And that gives us BC equals 0.88 meters. So then the area of the triangle ADD is 5 times 8.66 over 2, which gives us 21.65. And our ABC triangle would be AB times BC over 2, which is 5 times 0.88 over 2, gives us 2.2 meters squared. So then our W is equal to 18, which is our unit weight, times the difference in our areas of triangles, which is 21.65 minus 2.2, which gives us a value of about 350 kilonewtons per meter. So then we go back to our equation here. Factor of safety is equal to, our cohesion is 50, times our length, which we said is 10, plus our W is 350, times cos of alpha, and we're saying alpha here is the slope of the fail face, so 30, cos of 30, tan of our delta, and delta in our question is provided here at 10 degrees, so over W sine of alpha, so W is 350, sine of alpha was 30, which gives us a factor of safety of 3.16. So that's part A. It's asking for the factor of safety. Now, similar to like the last stability question we had, they want to know what the maximum allowable height is.